So in continuation to our yesterday's lecture, we'll be looking into Radarsat. Okay, so as you all are very much aware, okay, so this Radarsat is basically used for sensing. Okay, so it can be either your with respect to weather or with respect to ocean. Okay, so all this stuff are looked into, and it is monitored. Okay, so can someone tell me the importance of using a terrestrial network and a satellite network? You can unmute and respond. Terrestrial network is the normal networks that we use, and how do you differentiate that with your satellite network, satellite mobile services? Varun? So how is satellite mobile services more beneficial, or does it have a downside? Ashika, can you answer that question? Yes, you can unmute and respond. That's fine. Wireless and less transmission losses. Uh, okay. Anything else that you can add, Varun? You can unmute. You can unmute and respond. Anybody wants to unmute and respond? Nishmita, Akshaja, Kishan. Okay. So the coverage here with respect to your satellite mobile services are higher. Okay. So it's not only capable of serving a specific region, okay, but then it is capable of serving probably an entire country and the neighboring as well. Okay. So that's the advantage of having a satellite service. So during emergencies, these can be used not only for the purpose of communication, but also, for the purpose of security. Okay, so all this plays a very important role. So we had seen with regards to Radarsat, okay, as to it was launched. First version was launched in '95, okay, and the second one was launched in 2006. Now, as I was mentioning, okay, for a launch of a satellite, okay, you need about 8 to 10 years. Okay, it's a lot of work involved, the circuitry, the building. I think probably you can just imagine, okay, the complexity involved in designing a satellite. Okay, the sensors involved, each sensor should be checked if it's working fine, and then you can actually uh, think, okay, or you can imagine as to how complex things are. Okay, so it will actually take a lot of time in launching a satellite. Okay, so some of the objectives that you can look into is not only with regards to communication, but also with regards to research, okay, with regards to data that is available, okay, and with regards to how much of mm, you know uh, pollution that is happening. So all that can be looked into. Okay, so it can map and it can extract data, and it can send information to researchers. Okay, so what's the advantage of this? With a lot of data, we can understand as to how the future is going to be. Okay, what changes needs to be done in the present in order to change the future, right? So analysis can be done. So with the help of analysis, we will be able to understand, okay, as to the present available resources will be able to sustain for how long, for how many years. For example, if we are using petroleum, okay, at this rate, then for how many years it's going to last? Are we going to keep it for our future generation, or are we going to look for alternative sources of energy? Okay, so all these analysis can be done with the help of satellite. Okay, then communications is one such field, okay, where satellites do excel. Okay, it provides resource management and maritime safety. So this is with regards to your ships. During navigation, they can actually use, you can even check as to how far is the iceberg, how big, how dense. And with navigations, it's going to help you a lot. Okay, next, we'll be looking into the applications. Okay, it can be asked in your examinations. What are the applications of Radarsat, or what are the downsides, okay, of Radarsat, and what are the objectives? All this can be looked into. So as I told you, it can map the sea, okay, sea ice, then iceberg detection, forest management. How does it help in forest management? Can someone tell me? In forest management, how does it help? Bhavana, how does it help in forest management, your satellites? So we will be able to look into how much of trees have grown. Okay, so we can also check the analysis. Okay, we can check the data, and we will get to know as to how much of afforestation or deforestation is happening. So accordingly, we can judge as to if the forest is growing dense or is it growing thin. So with the help of these satellite imagery, satellite mapping, okay, we can actually look into this information, right? So with regards to shipping and fisheries, okay, how shipping is done, okay, how with regards to the weather, okay, and where more fishes are available, which weather is more favorable, okay, what is going to be the weather for another week, is there going to be a cyclone, okay, how is the weather going to be? All that is going to help with regards to the satellite. Ocean feature mapping. Okay, now when you think of this ocean feature mapping, okay, you can think of how rich the corals are. Okay, do you have the corals reducing everything, okay, based on the uh, you know, color image, okay, image color, you can actually identify its contents. Next, the oil pollution. Okay, most of the factories, they let out their industrial waste into your water body. So due to which, it's going to pollute. Okay, it's going to pollute, and because of which there can be the aquatic animals or aquatic bodies will be affected a lot. So that also can be monitored. Then see, ultimately you can think of satellites application is wide range. Okay, it's not only suited for just one specific mm, reason, but then there is multi-purpose. Okay, then crop monitoring. How crop monitoring, it can help in giving you the weather updates. okay, and how the crop is growing. So images can be taken and analyzed. You have a lot of algorithms which looks at these images and gives you proper information. Okay, then you have forest management, we have discussed. Land use mapping, okay, how the land is utilized, is there any acquisitions, okay, any legal mm, you know you can actually give this data to your authorities, local authorities, and check, okay, they will be able to check if, if the boundaries are properly maintained, everything. Okay, so this images can be blown up, it can be zoomed in, and it can be checked. Then geological mapping, of course, we all use that for our day-to-day purpose, the navigational purpose. Then topographic mapping, as I was mentioning, okay, they are trying to even map the universe. Okay, I don't know how many of you are aware of this. You can just look into it. They're trying to map the universe just like how you have map for our country, okay, or for our planet. Similarly, they are going to have the mapping done for the outer space, right? So applications can be n number. So these are some of the specifications for Radarsat. Okay, it is in LEO region, which is low Earth orbit, and the altitude is about 800 kilometers, and inclination is about 99 degrees. Then the period it takes for rotation is about 100 minutes, so close to 2 hours, and the repeat cycle is 24 days. Okay, so after 24 days, the cycle continues. So these are, some more information that you can actually look into, and you can see that the applications are n number. Okay, the orbital patterns or parameters are similar to those for NOAA. So this is nothing but your National Oceanographic and Atmospheric Administration. Okay, so this is NOAA. So they are dealing with oceans, the atmosphere, and how they are dealt with. Okay. Then, in particular, the Radarsat orbit is sun synchronous. Okay, so which means it is in sync with the movement of sun. It's not geosynchronous. Geo means Earth. Okay, so but then it is in sync with the sun. Then it carries C-band radar as a sensing mechanism. Okay, so C-type frequencies are used. These are much lower than the Ku band frequencies. Then these satellites carry a wide variety of instruments. Okay, so the soil testing, the moisture, and what kind of material, how much is the carbon content. Okay, you have something called carbon dating. Okay, so based on this carbon dating, you can actually find out what is the age of a particular uh, sample. Okay, although it is known that C-band radar uh, is not the optimal sensing mechanism for all the applications, but then it can operate in darkness and it does penetrate cloud. So that's the advantage. With Ku band, we have atmospheric losses and we have rain attenuation. When it comes across water molecules, then all that happens. There's a loss that could occur. But with this C band, okay, that's the advantage. It can penetrate through clouds and there is less loss. Much of the sensing is required at high latitudes where solar illumination of the earth can be poor and where there can be persistent cloud cover. So wherever it is densely covered with clouds, so in that cases, this C-band frequencies will help us in remote sensing. Okay. So the important point that you should remember here is the orbit is described as dawn to dusk. Okay, which means he can always see the satellite, okay, with respect to the sun. for the ascending and descending passages, because this is sun synchronous, right? This is not with respect to the earth. So maybe in one country, if you're able to see now, the satellite is in view in the other country after some time, which means at, after 12 hours. So which means the satellite is always in view. It may not be in the same country, but then it's always in view. Okay, that's what means to say. So this concept is referred to as dawn to dusk. Okay. So if a question is asked, then you can answer. These lines can be your answer. With radar sensor, it is not necessary to have Earth illuminated under satellite. The sun's rays reach the orbital plane in a broadside fashion. So since this is in view of sun, we have an added advantage. What's the advantage? There is no eclipse that happens. Maybe if it happens only for short duration, because it's always in sync with the sun, right? The main operational advantage is that the radar becomes fully dependent on solar power rather than battery. So this is very important, right? So it is fully dependent on solar power rather than battery power. Okay. So during both the ascending and descending passes. Okay. What is this ascending and descending passes during the days and nights? For the satellite, there's no day and night. Okay, but then it changes its uh, position. Since there is no operational need to distinguish between the ascending and descending passes, nearly twice as many observations can be made than otherwise would be possible. So since this satellite is always in view, okay, so we will be able to make the best use of it because it's always in view, and we can extract more data from it. So it is estimated that you can take about twice the data from this radar sat, just because it is always available. Okay, and the usage of battery power is less. It's fully reliable on solar power because it's in sync with the sun. So which means the sun rays always falls on it. Since the sun rays always fall on it, the solar cells are charged, and it is always powered through solar. Okay, so that's the advantage. Okay, the downlink periods for data transmission from radar sat will take place at times well removed from those used by other remote sensing satellites. Okay, so a lot of data can be extracted. As I told you, it's about 2x, okay, 2 times the data that you can extract from the other normal satellites, okay, because this is sun synchronous. The downlink periods for data transmission from Radarsat will take place at times well removed from those under by other remote sensing satellites. So a lot of data. Further advantages stated by the Canadian Space Agency are that the solar rays do not have to rotate. Okay, so which means this satellite will have the solar wings, right? So this solar wings, okay, does not have to rotate in view of the sun. Okay, it doesn't have to go in this direction, or this doesn't have to come in this direction. The solar panel that I'm talking about. Okay, so it can always be in the same direction. Why is that so? It is because it is in sync with the sun. So the solar rays are always falling on this, and it doesn't have to rotate. Okay, it can be stable in the same direction. Okay, no need to rotate. But unlike other satellites, okay, the solar wings needs to rotate. Okay, they need to be in view of the sun's rays. But there is a disadvantage since it's always exposed to sun. Okay, heat management or thermal management is very much necessary. Okay, and the spacecraft design is simple and it provides more better power raising capability. So you had that roll, pitch, and yaw, right? So those would not be necessary for the wings for the solar panels. With this particular dawn to dusk orbit, the satellite will be eclipsed by the Earth in the southern hemisphere from May 15 to July 30. Okay. So there will be a certain amount of time where there can be a certain eclipse for some amount of time. The eclipse period changes gradually from 0 to a maximum of about 15 minutes and back again to 0. Okay. So the battery backup is actually not needed, because it's for a very short duration, solar cells can be utilized. But if in case the levels goes too down, then immediately the batteries are utilized, but it's very rare. Okay, and they are not using lithium ion, but they are using nickel cadmium. Okay, so these are some high performance batteries. Okay, so this was the diagram that we were talking about from May 15 to July 30. Okay, so maximum you can see that it's about 15 minutes, 15 minutes that it's going to have the eclipse. Apart from that, it's all fine. Okay, it keeps going. uh, and as mentioned, okay, you don't have to really rely on your battery. Okay, so that happens from May to July. So it varies from 0 minutes to a maximum of about 15 minutes. Okay, so this is the image. Okay, so these wings do not have to rotate, they can just be stable. Okay, and here is your payload. Okay, your solar array, then your main module, the housing module, where all the sensors are housed, then your antennas. Okay, right. So the Radarsat is a comparatively large spacecraft. The total mass in orbit being about 3,100 kilos. So it's a huge amount of weight that your radar sat is, because it carries a lot of sensors, it carries a lot of antennas. So as the number of instruments, testing equipments increase, the weight also does. The radar works at a carrier frequency of 5.3 gigahertz. Now, as I mentioned, this is going to be in the C band. Okay, it's not going to be in the KU band. Now, the reason why we are using this is because it can pass through the clouds and there cannot be any kind of disturbance that can occur. Okay, but if you're using a higher frequency range, higher frequency band, then that can actually hit through the clouds and there can be losses, right? So these advantages are to be kept in mind. So this can be modulated with 3 different pulse widths, uh, depending on the resolution requirements. So as you all know, how you have this pulse width modulation, PWM. Okay, based on the amplitude of the signal, your width of the pulse also does change. So 3 different levels can be kept: low, medium, and high, for the purpose of this pulse. Okay. Then the SAR operating modes. Okay, we will actually see in a different figure. I will show you this. Okay. Different beam configurations can be achieved giving different resolutions. Okay. So as I mentioned, you can use low, medium, and high for this purpose. And using those, you can check that it can be varied for different kilometers. Okay, just have a look at this diagram, and you can actually see the footprint, okay, that it can actually cover. It completes 14 and 7/4 revolutions per day. Okay, so per day there can be revolutions about 14. So here, if you can see, if it's standard beam, okay, so it can range. The range is about 500, and the difference is only with regards to the beam. Okay, the spot beams. So each can cover about 500 kilometers. And as you see, wide beam, okay, wider area can be covered. Then these are pinpointed resolutions, okay, where you can pick up a specific uh, area, and that can be actually scanned. And you have scansar, okay, where your footprint is much higher. So if your footprint is much higher, it can actually scan through a bigger area. Okay, then you will have something called experimental beams. So these are in the range of 300 kilometers. All these that you see are in the range of 500 kilometers, and these are experimental, which can be with 300 kilometers range. Okay, so these are nothing but your SAR operating modes. So different operating modes, based on different width of the pulse, it can be varied. Okay, so these are some of the SAR modes, okay, that we have seen: operational, high resolution, experimental, scan SAR. Okay, so it can change. Okay, it can change with the coverage ranging from 1 to 500 kilometers. Okay, so operational, then based on the width of the beam, the kilometers also does change. So here you can have a look length by width, okay, L by W, and this is 28 by 30, 10 by 10, 100 by 100, and the angle, okay, the angle at which it is the spot beams occur is 20 to 30, 20 to 50. So we can take probably about 30 as 30 to 35 as our midpoint, and 20 to 50, yes, as I mentioned, 35. Okay, so all these modes you can probably put up in your scripts when a question is asked with regards to Radarsat. Okay, so for our last slide, okay, we can just think of radar 1 and 2. Okay, so this radar 1 and 2 has same orbit and repeat cycles. Okay, Radarsat. So even though they were designed about 10 years apart, okay, the speed and the repeat cycle have maintained, they have tried to maintain constant. Then radar 2 has additional capabilities for imaging. Okay, so that's one advantage. See, as you keep on moving from one satellite to another, okay, so what is going to happen? The capabilities also will increase. The number of facilities, the type of instruments will also increase, right? The radar resolution with radar 2 is 2.5 to 4.5 meters compared to over 9 meters. So resolution wise, which means you can have pinpointed spot beams with respect to radar 2 sat. Okay, radar sat 2. So you can just imagine it's about 2.5 meters, okay, compared with 9 meters, right? So the spot beam, okay, so this beam that I'm talking to you about is very much less. Fine beams, okay, fine beams are possible. Now all that was possible only because of the type of materials, okay, that was employed in the satellite. So radar 1 uses horizontal polarization, and with radar 2 they try to employ the vertical one also. So as and when the newer version of satellite is launched, we try and make sure that these are of higher grade, better quality, good batteries, better battery backup, The chemistry of the battery is changed, the circuitries, sensors, then fine-tuned outputs, ranging. Okay, all these are improved as they go from an lower version to a higher version. Okay, so we will see another few more concepts. Okay, probably in our upcoming classes as to how GPS works and all these things. I think we all are very much aware, right? So we will just look into this information, okay, in our upcoming lectures. So students, any doubts up to this point? Any doubts do you have? You can actually unmute and you can ask me questions. Any doubts? Okay, fine then. So we will catch up in our upcoming lecture, okay, with regards to different other applications of our satellite.